What is the optimal sampling temperature for an LLM on problem-solving tasks? When we first began this research project, large language models were still relatively new. There were many questions about inference hyperparameters like sampling temperature, top P, top K, and repetition penalty. AI engineers and researchers wanted to know what sampling temperature they should use for their applications in research, and there was no shortage of opinions about the best sampling temperature for specific tasks. For our research on AI agents, we also needed to know the answer to this question. However, we didn't want to rely on guesswork or gut instinct like others had done before. Instead, we decided to answer this question definitively using an evidence-based approach. Hello, I'm Matthew Renze, AI researcher consultant and graduate student at Johns Hopkins University. In this presentation, I'll discuss our research on the effect of sampling temperature on problem solving in large language models. Sampling temperature is an inference hyperparameter for large language models, also known as LLMs. It controls the randomness of the LLM's output. It's essentially a modification of the softmax function shown on screen, where tau is a constant temperature. Changing the temperature adjusts the resulting probability mass function for each potential next token in the LLM's output. A lower sampling temperature generates output tokens that are more deterministic. A higher sampling temperature generates output tokens that are more random. As a result, many people conceptualize higher temperatures as more creative output. However, higher temperatures also lead to a higher likelihood of model hallucination, statistically plausible yet factually incorrect responses. In the context of solution space search, temperature can be seen as a trade-off between exploring or exploiting possible solutions in the solution space. Higher temperatures explore the solution space more broadly. To answer our research question, we created an experiment involving 9 large language models, 5 prompt engineering techniques, 10 exams from various problem domains, with 100 questions randomly sampled from each exam for a total of 1,000 questions. For each model, prompt, and question, the LLM answered the question 10 times while sweeping across sampling temperatures from 0.0 to 2.0 in increments of 0.1. We ran a subset of this full experiment due to time and cost considerations. We used 9 of the most popular LLMs available at the time. This included proprietary models like OpenAI's GPT-4, as well as open source models like Llama 2 70B. We used a set of 5 prompt engineering techniques. These included a baseline prompt with no prompt engineering, as well as common prompt engineering techniques like domain expertise, self-recitation, chain of thought, and a composite prompt which included all 3 prompts plus self-criticism. We used 10 popular multiple-choice question-answer benchmarks for LLMs. These MCQA benchmarks covered various problem domains including math, science, law, and medicine. For each problem, the LLM was given a system prompt. This provided the LLM with general instructions on how to answer the multiple-choice question. Next, the LLM was provided with a single example problem and example solution. This helped the LLM better understand the instructions and the expected output. Then, the LLM was provided with the problem to be solved. This included the topic, the question, and possible answers. The LLM would then attempt to solve the problem. Depending upon the type of prompt engineering being evaluated, the LLM's response may have included a recitation of its existing knowledge on the problem being solved, a chain of thought containing step-by-step reasoning to a solution, a self-criticism of its thoughts to identify any errors, and a final answer to the question. After the LLM attempted to answer the question 10 times, its answers were compared with the correct answer. A score was calculated as the number of correct answers divided by the total number of answer attempts. After each experiment run, the final score was computed as the average correct answer accuracy for all questions. Other metrics were also collected, including the number of tokens generated, the runtime duration, and the cost per response. We used a Kruskal-Wallis test to evaluate the statistical significance of our results. Specifically, we looked for any changes in accuracy as a function of temperature. We chose Kruskal-Wallis because the data, that is the correct answer accuracy, were not normally distributed. Rather, they were bimodally distributed with centers at 0 and 1. To answer our research question, we plotted accuracy by temperature for GPT 3.5 using the chain of thought prompt on the 100-question exam. On the x-axis, we have sampling temperature from 0.0 to 1.6. On the y-axis, we have the correct answer accuracy. As we can see, accuracy remained stable from 0.0 to 1.0. After a temperature of 1.0, the accuracy rapidly deteriorated until the LLM produced no better than random guesses at a temperature of 1.6. We also performed a quantitative analysis of the data using GPT 3.5 with the chain of thought prompt on all 1,000 questions across temperatures from 0.0 to 1.0. The Kruskal-Wallis test yielded an H statistic of 10.439 with 10 degrees of freedom and a p-value of 0.403. At a significance threshold of 0.05, all changes we observed in performance as a function of temperature were not statistically significant. To generalize these results across LLMs, we analyzed the data by model, once again using the chain of thought prompt and the 100-question exam. As we can see, the correct answer accuracy remained stable across all temperatures from 0.0 to 1.0. To generalize these results across various types of prompt engineering techniques, we analyzed the data by prompt. As we can see, the accuracy remained stable across all temperatures from 0.0 to 1.0. And to generalize these results across problem domains, we analyzed the data by exam. Once again, the correct answer accuracy remained stable across all temperatures we evaluated. Finally, we performed a series of diagnostic tests to further support our results. For example, we analyzed text variability as a function of temperature. As expected, text similarity decreased as the temperature of the LLM increased, and then rapidly dropped off after a temperature of 1.0. This corresponds to our intuition that higher sampling temperatures produce more widely varied output. Our results indicate that changes in sampling temperature from 0.0 to 1.0 do not have a statistically significant effect on problem-solving performance. So, we recommend always setting your LLM's temperature to 0.0 for problem-solving tasks. This maximizes reproducibility without compromising accuracy. In addition, it helps avoid the inevitable drop-off in performance that occurs beyond a temperature of 1.0. And it minimizes the number of output tokens necessary to reach a correct solution. However, there were several limitations to this study. For example, we only tested 9 LLMs, 5 prompts, and 10 problem domains. Other LLMs, prompt engineering techniques, or problem domains may have led to different results. Also, our test set only included 1,000 problems. A small sample size may have biased our results. And we only tested a single inference hyperparameter. Modifying temperature in combination with other inference hyperparameters like top P, top K, or repetition penalty may have produced different results. Our findings have direct implications for AI engineers. This knowledge will save time and effort in determining the optimal sampling temperature for specific tasks. It may also reduce unproductive debates in the prompt engineering community. In addition, these findings also have additional insight for AI researchers. Our results show that LLMs are not more likely to hallucinate in ways that lead to incorrect solutions up to a temperature of at least 1.0. And higher temperatures do not improve solution space search in ways that lead to correct solutions more often than lower temperatures. Going forward, we recommend additional follow-up experiments. First, we should replicate these results with other LLMs, other problem domains, and other problem types to further generalize our findings. Second, for each LLM, prompt, and exam, we should extend the range of temperatures beyond 1.0 to determine where the performance begins to deteriorate. And third, we should perform a more in-depth error analysis to further support these findings. Finally, I'm happy to report that our results have been independently replicated by Michael Go, a data scientist at Ticker. His experiment led him to the same results and conclusion. In this research study, we empirically investigated the effects of sampling temperature on the performance of large language models on various types of problem-solving tasks. Our results indicate that sampling temperature in the range of 0.0 to 1.0 does not have a statistically significant impact on performance with multiple-choice question-answer problems. As a result, we recommend that you always set your sampling temperature to 0.0 for problem-solving tasks unless there's a compelling reason to do otherwise. To learn more, please see our research paper in GitHub repository. Thank you.